Humboldt Fellow here in Göttingen, and then will be a professor at Zurich starting in the fall. He's going to speak on Galois cohomology and Brauer.
Yeah, so this will be a series of 5 lectures that by the end will allow you to compute Brauer-Manning obstructions and thereby obtain examples of Diophantine equations that violate the hosta principle. So let me start with motivation. The hosta principle Okay, so I think you heard about this in the first talk this morning. This is a principle that is satisfied in some cases. So if you have a Diophantine equation, let me just do an example. This is motivation, so this is not important. So for many examples of Diophantine equations, so we seek a solution in integers and non-trivial. So a very easy first thing to do when you look at an equation like that is to try reducing it modulo various numbers and try to see if you can get some kind of contradiction. So of course you have an integer solution. You may as well assume it's minimal in some sense, at least having no common prime factors to x, y, and z. So you try reducing modulo various numbers like 3, 7, 11, and for instance mod 7, you see that you have then an equation which forces x and z to be 0 mod 7 if you just try different possibilities. But then plugging back in, you see that the first and last terms are divisible by 7 squared, and that forces then y to be divisible by 7 as well. And so this violates the assumption of having no prime factors. And by this very easy test, you see that there can be no non-trivial integer solutions. Now let's just change one of the numbers and see what happens. So if you try to play the same game now, you see that in fact there are solutions, mod 3, mod 7, mod 17, and so easily it follows, or with only a little bit of additional work, it follows that this has solutions modulo every integer. And in fact, so the hosta principle. So first of all, what was observed by Legendre for equations of this form, and then later for let's get it Minkowski. If you have any homogeneous polynomial of degree 2, and if you can verify this sort of condition, then it will follow that there are, in fact, integer solutions. Then Q So this is, in fact, the correct way of expressing the fact that it has non-trivial solutions modulo every integer. That you have p-adic solutions, and also you also verify that there are real solutions. So obviously, as we saw there in the top example, if you fail modulo some prime or power of a prime, then you rule out the existence of integer solutions. But the implication in the other direction is a non-trivial statement, and it's a very important result. And it depends on very much on the shape of the equations that are given. So this theorem applies to homogeneous polynomials of degree 2, and in fact fails for more general polynomials, and we'll see some examples of that. So this just illustrates this principle, and I should point out that there can also be examples. So so more generally, we can work with any number field. So, I shouldn't. There is an analogous statement with Q replaced by any number field. So of course, I could have just as well said we seek rational solutions, because you can multiply by common denominators and get an integer solution from a rational solution. So for homogeneous polynomials, integer versus rational makes no difference. So, but now you can replace the field of rational numbers by any finite extension. And there's an analogous statement where you have now, instead of the reals and the p-adics, these become all completions of a number field. So in the case of Q, you have these completions, and in general, you have some collection of both Archimedean and non-Archimedean completions. So I'll say the hosta principle holds also for cyclic norm equations. So you have a number field K, you have a cyclic extension L, and you have some element here. And so you're trying to solve this equation for U in L. And we'll see and so we'll be studying counterexamples to the hosta principle. Now, so that statement there was from roughly the 1920s, even though the case of polynomials in 3 variables had been treated by Legendre in the late 18th century. So, but this more general statement came later, and then it's hard to say when exactly mathematicians first realized that such a phenomenon wouldn't hold in general, but at least what I see in the literature, what's considered the oldest example of counterexample to the hosta principle is from around 1940. So due independently to 2 people, Lind and Reichert. And it's a weighted homogeneous equation. So again, we see non-trivial solutions, and this has no Okay, so if you look here, you see that this is actually saying several things. It's saying that it has real solutions, that's obvious, and p-adic solutions for every p, that's not obvious, but can be shown very... It's weighted homogeneous. So the point is, if you scale v and w by some scale, and scale u, let's say by lambda, and you scale u by lambda squared, you get a new solution. So it behaves much like there, where so there's the obvious trivial solution, 0, 0, 0, and we just look for some other solution. And if there should exist a rational solution, and then by scaling you can make it an integer solution. Okay, so if I do want to show you this example, so I will take a few moments to convince you that it has p-adic solutions. for every p. And then we'll show you that it has no integer solutions. Okay, so now I will make most of you bored by reviewing facts about the p-adics, which I assume are familiar to everybody. So, so there's the p-adic integers. With quotient field, the p-adic numbers. And then there's something called Hensel's lemma, which, okay, you can think of it in several. You can think of it geometrically, as to say you have an algebraic variety over the p-adic integers, and you reduce mod p and take a smooth point, and it lifts to a p-adic point. Or just in terms of equations, if you have some polynomial, and let's say you have a solution f of x naught is 0 mod p, and so it's some statement like this, that if you have a smooth point, then it lifts. So for instance, which square roots? Let's say A. So should I first? Well, I should avoid. I should be a little bit smart. So I take a non-zero mod p, and so let's see, what is it? So for odd p, it's just saying A is a quadratic residue of mod p. So that's a direct application of that statement, because you solve mod p and then lift using, since the derivative here is 2x. So, but for p is 2, well, so I should say that, so ZP solutions can also be obtained when and so now, yeah, you don't have this statement, but you can essentially use the same method. So let me just work out this case. Take okay, so I've just written down the equation for x squared equals some number, that's 1 mod 8, and p equals 2. So then we take, so then you just write down something like f of plus something, I don't know, I mean, 2 to the k y or some such thing like that might give something good, I don't know. Let's just subtract. So I don't know, you have to sort of expand this, and so you get 2 to the k plus 1. I mean, no, I can't. Yeah. So what is it saying? That as long as k is at least 2, then you can make such an adjustment, and then you can change the difference as a multiple of 2 to the k plus 1. And so inductively, you can lift to increasing precision, starting with a square root, well, just 1 as your x naught, and then continue. Okay, and well, now, yeah, everyone certainly knows quadratic reciprocity, so there's no, well, but I think just to have it on the blackboard, well, as a handy reference, let me just waste some moments and put it on here. So Galois, of course, worked in Göttingen. So okay. Okay, so now let's see, what do I owe you? I owe you some p-adic solutions, and okay, so let's see, p-adic solutions. Take u equal to 0. W equal to 1. And B equal to the 4th root of 17. So 17 has a square root in Q2. And then that square root is, well, if you choose the appropriate square root, it'll be 1 mod 8, and so you take the square root again. So there is a 4th root. Okay, now let's see. P odd. Well, so there are 2 possible approaches. There's well, you can take P equal to 17, and then, well, I don't even know what it is. 1 over square root of 2. And then so you can get the existence of p-adic solutions directly from Hensel's lemma using the fact that when p is different from 2 and 17, that equation has what's called good reduction mod p. So it defines a smooth curve of the same shape modulo p. I mean, because it's weighted homogeneous. So it's a curve in weighted projective space. Anyway, it's an elliptic curve. I mean, it's a curve of genus 1, and so we know that such a curve must have points. And so, yeah, there's some general theory. So there exists QP solutions by Hensels. So using since and this is in fact always the case. So that means that there are only finitely many primes where you need to work. And for all the rest of the primes, you can just invoke some machinery to get the existence of solutions. So the testing of the hosta principle, at least the testing of the local conditions, the p-adic solutions, is a finite process. But it uses theory. I mean, now, if you're not familiar with this, then I'll also give a direct argument, or just by some ad hoc. I mean, I just wrote down some solutions. So when p is plus or minus 1 mod 8, then there's again, well, just like this. Yeah, because that's what this says. Yeah. And what else? P is 3 mod 8. Then we can do something like and when P. So yeah, of course, this being a quadratic residue or not is multiplicative. This is to be a quadratic residue modulo P, let's say. So for minus 2, well, you use both of these conditions, and you see that 3 mod 8 minus 2 is a quadratic residue. So what's left? P is 5. Then there are 3 possibilities. So one of so one of these is a QP solution. Okay, so now for, so now I just show you that there are no Q solutions. So suppose no common. Okay. So then, so if you just see what it tells you, mod 17, you see that U can only be one of the following choices: plus minus 3, plus minus 5, plus minus 6, or plus minus 7. So. In fact, exactly the non-quadratic residues. Okay, now for general P, let's say odd P. So now yeah, okay. If u is divisible by some odd prime, well, okay, 0 is not allowed. So, in fact, this p would have to be different from 17. So we have an odd prime, not 17, dividing u. Then, based on that equation, now the left-hand side vanishes mod p. So this u and v and w, well, they show that 17 is a square mod p. So if there were a common, let's suppose that 3 were to divide u, v, and w. Then I would divide v and w . Yeah, then the right-hand side would be divisible by 3 to the 4th. So that would, in fact, force u to be divisible twice. So now I divide u by 3 squared, divide v and w each by 3, and I get a smaller solution. Okay, so by quadratic reciprocity, yeah, P is a quadratic residue mod 17. Now, U is a product of a number of these primes, as well as plus or minus 1, perhaps 2. Well, minus 1 and 2 are quadratic residues mod 17, so they don't contribute. And every prime divisor of U is a quadratic residue mod 17. So U itself must be quadratic residue mod 17, which is just a contradiction to what we deduced previously. Yes, in this case. And if you have a more general equation, yeah, I mean, that's right. In this case, it's a curve, and so you have a curve, and you know its genus is 1, and so the has of A bounds. In fact, every genus 1 curve has a point. Now, if you had let's say, a higher degree equation, you'd have a higher genus curve. And then possibly for some small primes, you would have to check those still, because the has of A bounds would be too weak. You wouldn't. But for sufficiently large prime, then you would know by the has of A bounds that there are points. So it always reduces you to doing a finite amount of checking. Okay, so I think, yeah, we're happy with this example. We see it uses quadratic reciprocity. Now, I just want to restate things a little bit. There's something called the Hilbert symbol. And it's defined as follows. Non-trivial. Oh, so this is a, well, is a prime or infinity, which means so it's what's called a place. It's a completion. It denotes a completion of Q. So either a finite place or infinity. So of course, again here, we have the remark that, let's say it's a prime. If the prime does not divide, or is, well, as I've stated, that a and b are rational numbers, but if that prime does not show up in the numerator or denominator of a or b, then it's again a case where you have good reduction mod p. And so, you know, there exists solutions. So, or more directly by Chevalier's theorem, if a and b are integers, then ax squared plus by squared plus. Yes? Yeah. Yeah. So for 2, I don't care, because 2 is a quadratic residue mod 17. So yeah, I'm perfectly happy to have 2 dividing u as many times as you want, because it doesn't change that calculation to have a factor of 2. That what? No, here it uses all primes, all prime divisors of u. And then, yeah, using quadratic reciprocity, you switch it to mod 17. But it's combining information from all the primes. It's not purely a local calculation. Okay, so the point of this, the reason why I'm doing this, is just to give you a new language for talking about this sort of argument. So the Hilbert reciprocity law states that the product overall, so this means primes as well as infinity, all places of the value of this Hilbert symbol. I mean, by this remark, there can only be finitely many primes for which it takes the value -1. Now, if I can state, again, this is very much a review for most of you. You've all seen this. But I can state as an exercise for anyone who hasn't seen it to show that the statement of the Hilbert reciprocity law is equivalent to, or can be deduced from, quadratic reciprocity. And to restate that argument, in this example, using the Hilbert symbol, 17u, and so do one more. So let's consider the following equation. Again, it's weighted homogeneous. And so, yeah, this is due to Iskovsky, 1971. And use, so let's see, what do we have? Well, we have notice that the right-hand side, well, like if you bring V over to this side, then you see U squared equals minus 1 times V squared plus this times 1. So use which is equal to this one, Iskovsky. Maybe it's not Iskovsky. It's okay. Oh, is this for Iskovsky? KH? I don't know. Is that the... Is that better? Okay, maybe it's right. I don't know. Okay, so of course now, see the Hilbert symbol is multiplicative in each variable. Like let's say if you do A here and you put BC here, then it's just AB times AC. So it has a nice multiplicative property. And then here, so if this is 1, then these two are equal. Okay, so this, well, by the end of today, I hope we'll see that these can be viewed as Brauer group elements. So, see, okay, so up until now, this is just motivation. Perhaps I should have gone a little faster. So the topic for today was supposed to be Brauer groups and Galois cohomology. And, well, I should at least be able to talk about Brauer groups. Now, again, that's something classical, so I think most people here have seen Brauer groups. So, again, at the risk of causing a lot of boredom, I will recall Brauer groups. So let K be a field. And we consider finite dimensional central simple algebras, in general non-commutative. Okay, so this is I think that everyone knows what this means, but simple means having no non-trivial two-sided ideals. And central means that the center is K. And so there's a structure theorem due to Wedderburn. That such an algebra is isomorphic to a matrix algebra over a division algebra. So if we have two finite dimensional central simple algebras over K, then so is their tensor product. So it's also central simple algebra, and so is the opposite. So you take the algebra with the opposite multiplicative structure, and these define the multiplication and inverse in the Brauer group. For K, whose elements are classes of finite dimensional simple algebras. Up to what's called Brauer equivalence. The Brauer equivalence says that two algebras are Brauer equivalent if they're equal up to taking matrix algebras. So now, of course, look at the structure theorem. So A is a matrix algebra over division algebra, and so is B. So this is really equivalent to saying that the division algebras in each case are isomorphic. In other words, A is a matrix algebra over D, and B is also a matrix algebra over the same D. And so then each of these is just a bigger matrix. Yeah, so we just have matrix algebras over D. So in some sense, that you can, if you want to work with elements concretely, you can just work with division algebras. But every time you do a group operation, then you have to sort of reduce by writing it as a matrix algebra over division algebra.
Excuse me, when you say division algebra, you mean central division algebra?
Yes. Okay. So I didn't, okay, well, yeah, I put central there for some. Yeah, I mean, of course, it would follow, because if you look at Mn of D, the center is the center of D. So if you have such an isomorphism, then D has to have center equal to K. And again, the same remark, what I was saying here. So concretely, in terms of elements, the representative elements are central division algebras over K. So let me just write down an example. So first of all, fact. Then after taking a finite field extension, then you get a matrix algebra. So in particular, any central simple algebra has dimension that's a square. Okay, so let's look at some examples. Well, by this fact, if K is algebraically closed, Brauer group is trivial. Now, theorem of Frobenius characterizes all non-commutative, essentially the unique algebra, the unique division algebra over R that's central is the class of the Hamilton quaternions. And so the Brauer group has order 2. No, sorry? Oh, sorry, this is a complete mess. If A is this is this abbreviation, finite dimensional central simple algebra, then there's a finite field extension, K prime of K.
The line after that.
In particular, the dimension of is a square. This is dimension. Okay, so I really should have covered more. Okay, so local class field theory identifies the Brauer group of the p-adics with Q mod Z. And then by global class field theory, there's a short exact sequence. And this is then more general also, arbitrary number fields. So here again, I'm using this notation where you sum over all places. So again, this is all primes as well as the place at infinity. And for a general number field, you have all valuations, both Archimedean and non-Archimedean. Okay, and just as a last example, you have quaternion algebras. So if you have A and B, let's say, assume that the characteristic is not 2, and then A and B are non-zero field elements, then you take an algebra. What a notation, I don't know. Let's just write it like this, AB. So this is an algebra with, you have I and J, and I squared is A, j squared is b, and I and j anti-commute. Yeah?
In the exact sequence, what is the projection map they are producing?
This one? This map here is the, well, it uses, so this is canonical. So each of these maps by the canonical isomorphism here to Q mod Z, and then for any, well, for the real place, you have a two-element group, and that maps to the two-element subgroup here. And so you just have the sum of local, it's the sum of all the invariants here. Okay, so I guess what I can say about this, so e.g. when k is r, then -1, -1 is Hamilton quaternions. And, well, then there's this help. So the Hilbert symbol is 1 if, well, A and B is 0. So this Hilbert symbol is exactly producing elements of the Brauer group. So if you have A and B rational numbers, then you think of this as an element of the Brauer group of Q, and the Hilbert symbol is telling you whether, when you pass to a completion, this element becomes the trivial element, or whether this element stays non-trivial. And so this sort of argument here will say that you get counterexamples to the hosta principle, or you have some kind of a way of understanding in a finer way the hosta principle by writing down elements of the Brauer group. Now, notice that here you involve some elements of the function field. So you think of it geometrically as a surface, and you have elements of the function field. So it's a Brauer group element on the surface. And then this kind of argument, well, what we saw using quadratic reciprocity, when it's phrased in this language, becomes an argument using Brauer group elements. Unfortunately, I didn't have time today for group cohomology, Galois cohomology, so I will start with that next time.